today's lecture on DC coupling, AC coupling, and pulse train. Understanding this concept is crucial for interpreting signals on an oscilloscope in automotive diagnostics. Okay, especially when you are working with different types of electrical signals. Okay. Now, coming on to the DC coupling. DC coupling displays both DC and AC signal, making it useful for observing a steady DC voltage with any added AC ripple. Take a small example. If you are testing a car battery during starting, DC coupling shows a flat line at around 12 volts. As the starter engages, the line drops to 10.5 volts. Once the engine starts, the alternator raises the line to around 14.5 volts. And any AC ripple from the faulty diode will appear a small oscillation on top of this line. Now coming on to AC coupling. AC coupling filters out DC, allowing only AC signal to be displayed. This is useful for observing the ripple voltage in a car's charging system without the DC component. For example, if you want to measure only the alternator ripple, AC coupling will show just the fluctuation, highlighting the potential issues with the diodes in the alternator. Take another example for AC signal measurement. An AC signals alternates above and below the 0 volts. To observe household 120 volts AC on an oscilloscope, you have to set it to AC coupling. The waveform shows peaks above 120 volts and below minus 120 volts, which translate to a range of more than 240 volts. Setting the volts per division to 50 volts will allow the full AC waveform to be seen within the screen's 40 volt range. Now, the next important concept, the pulse train. A pulse train is a DC signal that turns on and off in a series of pulses, often used in automotive electronics. For instance, fuel injectors and ignition system use pulse train to control on and off cycles, with each pulse representing an injection or spark event. This on-off pattern can be seen clearly on an oscilloscope. Here, there are two important terms associated with the pulse train known as the frequency and duty cycle. The frequency indicates the number of cycles per second and is measured in hertz, while the duty cycle represents the percentage of time the signal is on during each cycle. For example, in a fuel injector pulse train, a higher frequency at higher RPM increases the number of ignitions per second, while the duty cycle indicates how long each injector remains open. Here we can see using this diagram over here. So here take this as a, we can say, signal. Okay, in 1 second these are certain peaks and valleys. So a pulse train, which is usually an electrical signal that turns on and off or goes high and low in a series of pulses. Igniter and fuel injector pulses are the examples of a pulse train signals. Now, in this case, as I shown you earlier, the frequency indicates the number of cycles that takes place per second. The more cycle that takes place in 1 second, higher the frequency reading. Frequencies are measured in hertz, which is number of cycles per second. And 8 hertz signal cycle 8 times per second. Now here you can see there are 8 signals in 1 second. So here they have told us there are 8 hertz frequency signal. We look as 8 hertz means 8 cycles per second. Okay. Now next important concept is the duty cycle. Duty cycle is a measurement comparing the signal on time to the length of one complete cycle. As on time increases, off time decreases. Duty cycle is measured in percentage of on time. A 60% duty cycle is a signal that it's on 60% of the time and off 40% of the time. Another way to measure duty cycle is the dwell, which is measured in degrees instead of percent. Another important point, duty cycle is just a relationship between one complete cycle and the signals on time. The signal can vary in duty cycle without affecting the frequency. Okay. Now here in this last diagram, you can see this is nothing but a pulse width. A pulse width is the actual on time of a signal and it is measured in milliseconds. With pulse width measurement, off time doesn't really matter. The only real concern is how long the signal is on. This is useful test for measuring conventional injectors on time to see the signal is varied with the load it is changing. The pulse width is the actual time a signal is on, measured in milliseconds. The off time doesn't affect the signal's pulse width at all. The only thing being measured is how long the signal is on. Now, coming to the use of this measurement for the, we can say, fuel pump. And fuel pump is actually an electronic return-less fuel system. Is an example of pulse width modulation, pulse on and off with variable duty cycle. A solenoid activation is changing 10 times per second, that is 10 hertz, but on time varies. In this example, the duty cycle is measured in degrees. Okay. Now here in this diagram, you can see this is a representation of a duty cycle. The scope represents the on time, or this is one complete cycle represent over here, and in this complete cycle this indicates the on time of the fuel pump. Okay, now the scope representation of a complete cycle showing on time and off time. Now there is a meter which displays the on time duty cycle in percentage. Note the trigger negative symbol. Okay, now this indicates that the meter started to record the percentage of on time when the voltage drop start of the time. Now what happens here, this is a negative, this is, we can say this is the baseline and this is a negative. So from here it started to check and it stopped over here. So here therefore there is a negative sign over here. Now, as already discussed here, we can see in these diagrams, okay, on time ground control and on time, we can say this is the feed control mechanisms, okay, which are basically used in our automobiles, okay. Now, what happens, this triggering of the signals in the oscilloscope, we can have this important thing. But before going to that, we will discuss this pulse width phenomena one more time. As I have discussed, it is a measure of actual on time measured in millisecond. And these fuel injectors are controlled by using these pulse width signals. Now, in this case, here, when it is connected to this ground, so this indicates the on time, and when it is connected to the feed, means the fuel is supplied, it indicates the on time. So this is the complete cycle on the ground control circuit. The on time is the lower horizontal line. So this is the on time when it is connected to the ground. But when it is connected to the system, and when the feed is provided, so here the on time is the upper pulse of this horizontal line. So most automotive computer systems control the devices by opening and closing these grounds of the components, and according to it, the pulse train phenomena can also change. Now, this is an important concept. Just we have seen what it indicates, the triggering phenomena. Okay. Now, triggering stabilizes the waveform by starting the display at a specific voltage. For instance, if you see the trigger to 1 volt, the oscilloscope will begin to display the waveform whenever the signal crosses the 1 volt. This is useful for consistent display of periodic signals such as ignition pulses. Now here, one more concept, that is the positive and negative trigger slopes. Now the trigger slopes determine if the oscilloscope trigger on rising or falling. For example, in an ignition system test, a positive trigger slope would start the waveform to display as the voltage rises, capturing the moment the ignition pulse fires. Conversely, a negative slope will capture when the voltage drop after the pulse. Okay, so now here this is a, we can say, effect of this positive and negative slopes. Okay, one more thing which I want to discuss here, that in this today's lecture, see, we have seen the pulse width phenomena, duty cycle, frequency, which are very much essential in our controlling the components in automobile systems. Okay, so we have seen the oscilloscope trigger. Now in this trigger there are two positive and a negative trigger. The symbols of these are also shown in A and B. Symbol for a positive trigger: a trigger occurs at a rising positive edge of a signal. So this A indicates the positive trigger symbol, whereas a negative trigger occurs at a falling negative edge of the waveform. So this is the negative edge. Okay. Now, in summary, if you get for today's lecture, we have seen the understanding of DC coupling, AC coupling, pulse train, and triggering, which allows us to accurately observe and interpret waveforms on an oscilloscope. This knowledge is invaluable in diagnosing complex automotive electrical systems and ensuring accurate readings. I hope you have understood today's lecture. If any students feels any doubt regarding any of this concept, please feel free to drop me an email. So thank you for your attention.